Hey there. Today, Saki, Mahesh, Varain, Sean, and Sung Young will be discussing and presenting a swarm drone demonstration for our CYSE 425 Secure RF Communications class. We will go over our project outline, goals, background, challenges, implementation, the drones used, our architecture, scripts, a demonstration, a reflection, and lastly, a conclusion. For this project, our goal was to connect two Tello EDU drones simultaneously and have them move in sync as well as a sequential order. We did this by utilizing the Tello software development kit, Python, a Verizon router, and our laptops.
So our goals were to firstly demonstrate the swarm drone abilities in movement, and then secondly to demonstrate the swarm drone abilities in a pattern search. And this pattern search part is important for us to be able to do that without a pre-established infrastructure. So typically in modern applications that are currently available on a commercial and like industrial level, um, there is a lot of infrastructure required to actually ensure the swarm drone is able to operate as a swarm. There's a lot of infrastructure required, additionally, to conduct a search. So, what this means infrastructure wise is um, a lot of routers and other access points that can communicate with the drone and maintain consistent connection over long distances on a 2.4 hertz frequency. Um, and to actually have the pattern search uh, systematically go through and section out an area and have it all uploaded and have the drone like processing that data. That requires a lot of in-ground sensors. And this obviously is very costly. There's a lot of time and planning that goes into this. And for some of our applications of swarm drones, that's really not realistic. Um, so next slide, please. Okay, so this is our background on swarm drones and drones in general. So basically, drones are UAVs or unmanned aerial vehicles with rapidly expanding applications. Many of these applications require the use of multiple drones, hence the term swarm drone. Um, so we briefly discussed this in the previous slide, but to conduct something like a pattern search. So what I mean by that is a pattern of regular movement by the swarm to cover a certain amount of area. And in order to scan a certain amount of area for a specific marker or for a specific object or something that they're searching for. So this is all like pretty vague, but an example of an application of a pattern search would be something like a search and rescue mission. So if there's a natural disaster or some other adverse conditions where humans cannot enter an area or humans cannot explore an area, and there's no technology that is better suited for something like that. So this would be something like if a building has crashed, or if there's really hard to reach loose rock or loose land, and you need to search that area. This is where a swarm drone would be used. Um, and to effectively use a swarm, especially a swarm drone, having a centralized interface is really crucial. So this just means that you can have one place that's sending out the commands that has control over the swarm, and you are able to see that your connection is maintained. So currently, a lot of the approaches of implementing swarm drone solutions, whether it's search and rescue, whether it's something like conservation, like tracking endangered animals and having like 24-hour security, a lot of this requires a lot of financial overhead, a lot of time investment, a lot of money investment, and a lot of resources being involved to set up this infrastructure. So this infrastructure is going to include like on-ground sensors. It's going to include beacons that can amplify signals and stuff, because typically when you're using drones, the frequency and the hertz values are like 2.4 hertz, so it's not like for super long range. So having that infrastructure set up is really the only way to kind of guarantee reliability as having a solution of a swarm of drones. So a lot of these additional issues are really limiting the abilities of researchers and students and like industry professionals to really implement drones in a feasible manner. So that's where our whole project comes in, having that centralized interface, having that control, demonstrating the capabilities of a swarm of drones, and demonstrating the abilities of a drone. So this project's main goal is to suggest and develop and implement and show that it's all working without pre-existing infrastructure. So the next slide. And these are some of the challenges that we have run into. So firstly, I'll just start with the development. So as we were developing these scripts to have that movement, to have that pattern search, we were doing this across several different APIs. I'm kind of going back and forth the nomenclature and the kind of syntax and the way in which kind of singular drone objects were constructed. It differed pretty greatly between APIs. So just developing the scripts using that was pretty difficult. Um, Additionally, as we were testing, the calculations involved in those specific syntaxes varied greatly. A lot of it was using like an XY coordinate grid, but we were somehow doing this in a 3D axis, in a 3D space. So that was difficult to make sure our calculations were correct and that the drone was actually doing movements the way we wanted it to be done. And then additionally, we had a bunch of hardware inconsistencies. The battery would consistently die. It would consistently not charge. Somehow our charger wasn't working. Somehow we had a lot of issues with that. Um, the propellers were on the wrong way. They can only be on clockwise, but we put on counterclockwise ones. And then lastly, a really big issue that we ran into. This is kind of like an asterisk issue. It's we had a consistent error during curved movement. Um, and what this means is from our command and control, we're seeing that we're getting an error back. Like the drone is sending an error that it's not able to continue this movement. But eventually we got it to the point where it would do the movement, but somehow we were not able to um, avoid that error message. So that was a consistent issue that I feel is relevant enough to bring up. Um, and then some of the other issues we had with the hardware. Um, so the drones we've been working on in class, and in the drone competition are just regular DJI Tello drones. So these are not compatible with a swarm. So we have to get Tello EDU drones, which were very different. We had a lot of issues with delivery. They delivered a bag and no drone. Then they delivered the drone late. And then the battery issues, once again, consistently plagued us. Um, and yeah, now we will move on to the next slide.
All right, thank you, Mahesh. So, this is our implementation. This is just kind of the general process that we followed when conducting this project. The first step involved a literature review. This was just kind of us conducting open source research. We wanted to see how people were accomplishing a swarm of drones otherwise with the current technology and infrastructure. And again, as Mahesh mentioned, we did find that the majority of the research that had been conducted so far did rely on a pre-established and external infrastructure of sensors and modules in order to gather information like like speed, direction, velocity, GPS location, things like that. After we conducted our research and we decided on our best approach, we then had to set up our environment. Our environment involved the use of an Ubuntu VM along with an external wireless interface so that we could connect to the access point, which we'll go into further detail here shortly. After that, we started beginning our script development. We did this by pulling from many of the resources that we gathered during the literature review and research phase. So basically, just kind of looking at the scripts that people had built before and kind of pulling little bits and pieces here and there and building something that really worked for what we were trying to accomplish. Um, Throughout this process and after the scripts were developed, it was kind of an iterative process, but we would then test them. We would conduct testing, and we would see what went well, what didn't go well, and then make changes to that as well. And then finally, the last step was the replication step, which is when we conducted our demonstration and recorded it. And I believe that, yeah, that should do it. Next slide, please. So our equipment configuration. Um, Again, as Mahesh mentioned briefly, there is a difference between the traditional Tello drones that we've been using in our class thus far and the Tello EDU drones. The primary difference is that the drones we've been using in class are only capable of being used in what's known as station mode. And station mode is essentially where the drone will act as as a station. It produces its own Wi-Fi network, which you then connect to issue commands. Alternatively, the Tello EDU drone has the station mode capability, but also has an access point mode. And the access point essentially allows the drone to function as a client and connect to an external router. And that's kind of what we were going for in our project, because we didn't want to replicate some of the other methods which involved using multiple wireless adapters. We really wanted to implement a way of controlling multiple drones using a single interface and without relying on a lot of external infrastructure. The router that we used for this project it's a Verizon FiOS router, and again, it's integrated with a 802.11 A through Z, and then more specifically, we did need to make sure that the router was had the 2.4 gigahertz channel enabled, because the teledrones only communicate via 2.4 and not 5 hertz. And now I believe I'm going to pass it on to Sean so he can discuss some of the setup and architecture.
Hello, so this is our architecture setup. We're connecting to the drone and setting everything up. For our project, we did everything in a Ubuntu VM with a wireless adapter and a router. So after enabling our adapter in the VM, we then turn on the drones and connect to them individually. After connecting to them individually, using the script setap.py and our router credentials, we can set the drones to connect to the router on the next reboot. Then, from the router's user interface, as shown in the picture, we can easily gather the IP addresses of the drones, which is necessary in order to send commands. And after this, we then reconnect to the router with our adapter, and using the scripts we developed, we can then successfully run the drones in a swarm formation.
In this script, we have to specify the IP addresses of the drones, and this is easily scalable, as all you have to do to add more drones is to just add their IP addresses. First, in our script, we specify the IP addresses of our drone and had them connect to the router to take off. From there, the first command we gave them to do is to make a vertical circle. To do this, we first make the drones fly a little bit higher, and then in the curve command, we have to specify the 2 points that we want our drones to fly a curve on. Next, the drones move forward sequentially, one after the other, and face each other by rotating one by one and then doing a backflip. Then we have them do the curve command again, this time with the horizontal semicircle so that they switch spots. The drones then face each other one more time, move closer to each other, and finally they spin before landing. This is our drone search script that we made for our second demo. In this script, we have to specify the serial numbers of the drones, and this information is found directly on the drone. Our code is relatively simple since we use a flytele library. First, in our script, we specify the serial number of the drone. We then commanded the drone to take off and start the search command, search spiral. How search spiral works is that we first specify 6 parameters: the distance, how many spirals, the height of the search, the speed of the drone, which pad we want to land on and find, and which drone to command. In our command, we also specified the pad M-2. This means to find the nearest pad available. How this command searches is that it searches in a square. Having spirals set to 3 means that the drone will do 3 spirals to search for the pad, and each time the drone is unsuccessful in finding the pad, the drone's spiral gets larger. The drone can only then successfully find the landing pad if it's directly over it, and once it does find the landing pad, it begins to land. We originally planned to showcase both drones doing a search, but this was inconsistent as we only got this to work one time and we did not record it.
And this is a video of our demo.
Bam!
So here is our reflection. We first used a Tello drone instead of Tello EDU drone, so we were not able to start earlier, and we had waited a few days to get the Tello EDU drones. Through this project, we gained wireless communication knowledge, and the researching relevant topics aided understanding, and lastly, we were able to collaborate through adversity of the project. And in conclusion, drone swarming has broad applications such as entertainment, security surveillance, search and rescue, and etc. It was really a good project to exercise in coding drones, work with team, and learn RF communication. So in the future, we plan to add support for searching for a landing place for multiple drones as we work capable of performing it for a singular drone. And that's for our project. Thank you.